Okay, so during last lecture, we discussed about Cartesian coordinate system. As per as concerned with Cartesian coordinate system, we have seen that whenever the coordinates x, y, and z are present, then that kind of system we are representing in the form of Cartesian coordinates. So, any rectangular block which is three dimensional, so that can be expressed in terms of three dimensions, that is x, y, and z. But if we consider the geometry like cylinder, cone, etc., then these are considered to be solid of revolutions. So these kind of bodies which are considered to be solid of revolutions, so for them we can't express all the dimensions in terms of x, y, and z. Besides, we will have to represent these dimensions in terms of radius, then thickness z, and angle theta. So the parameters in case of Cartesian coordinate system are x, y, and z. However, the parameters in case of polar coordinate system is r, theta, and z. So that is the basic difference, that based on the shape, the Cartesian coordinate system is expressed with three coordinates, that is x, y, and z. But in case of polar coordinate system, we require to represent that in terms of r, theta, and z. Is it okay? So this is the figure which represents, as usual, we are considering the small element. Likewise, here also we have considered the small element, and that small element represents the uh, whatever three dimensions which we consider here as a polar coordinate system, because in case of polar coordinate system we are considering r as a radius, theta as an angle, and z as a thickness. Okay, so this is the thickness z, then this is radius r, and this is angle theta. So radius, angle, and thickness. So these are the three parameters with which we are presenting the polar coordinate system. Is it okay? So likewise, as we have taken example in case of Cartesian coordinate system also, the stresses in different directions that we have represented in terms of their uh, in which direction they are relying. Now, for example, here if we consider the case of sigma RR, which is presented here, which is shown here. Here you can represent this sigma RR. So definitely that sigma RR is the stress along radial similar portion sigma ZZ. So sigma ZZ is here the stress in the direction of this z direction. Is it okay? In the along the thickness, here we consider this is the along thickness. Here we consider this as along the radius. So along the radius, and along the thickness, and along this angular direction. Here if we represent, this is z axis. So vertical axis is considered to be z axis, and in this z axis, here the stress, the line parallel to this z, so that is represented by sigma zz. The stress along z is considered to be sigma zz. Similarly, stress along radial direction is considered to be sigma rr, and stress along angular direction is considered to be sigma theta theta. So let us try to represent first of all the different stresses in different directions, inside which the first is the stress along radial direction, then stress along vertical direction, and stress along angular direction with their regular notations. This is sigma rr, this is sigma zz, and this is sigma theta theta. Is it okay? Which is the stresses in purely radial, vertical, and angular directions. Is it okay? Now we have seen in case of Cartesian coordinate system that the stresses, for that purpose, if we take one example, that here we have represented the sigma theta r. Now this arrow which is moving in the direction of angle, so this sigma which we are representing with theta r, so for that if we take direction of this arrow, then that arrow is in the direction of angle. However, this is the component of sigma rr. So sigma rr represents the stress along radial direction, and its a component along angular direction is represented by sigma theta r. Is it okay? So the component of a radial direction along angular direction is represented by sigma theta r. So the meaning, the notation used, sigma theta r is the component of a radial stress along angular direction. Is it okay? The component of a radial stress along angular direction. So that we are considering to be sigma theta r. Similarly, if we consider this vertical stress, then this is the component of radial direction in vertical direction. Okay, so sigma zr. So this is the component of this stress in a radial direction along vertical direction. So this is considered sigma zr. Now, three component of stresses we can see here. Sigma rr is stress along radial direction, then stress component of stress along angular direction, and component of radial stress along vertical direction. Similarly, if we take example here, sigma zz is the component of stress in vertical direction, but its component along radial direction, which is represented by sigma rz. So sigma zz is purely in vertical direction, but the component of this sigma zz along radial direction is given as sigma rz. Similarly, here component of this vertical direction stress along angular direction is given as sigma theta z. So same thing we can understand here also. So this arrow which is shown by sigma theta theta here, so component of this sigma theta theta along radial direction is sigma r theta, and component of this stress along z direction is given as sigma z theta. Is it okay? So same thing, same type of stresses may be present on this inside curvature portion. At the same time, the opposite surface, which is not seen in this figure, but present on the opposite side, because here we are able to observe three surfaces, and remaining three surfaces we are not able to observe, out of which this inner curved surface, then the backside surface, and bottommost portion here. So these three things we are not able to observe here, but on these surfaces also these stresses are present. Is it okay? So whatever the component we have seen in this along these three surfaces, equal and opposite components are present on the opposite surfaces. Is it okay? So here we can see here the same figure which was previously shown as a three-dimensional figure is now represented as 2D figure. Okay, here you can see this figure as a 2D figure, and then Will be able to understand here that this vertical line, this arrow, horizontal line, this arrow. So that is this three-dimensional case with these two arrows, which is shown at the bottom here. So Z is not considered. By neglecting that Z, or here you can consider this as one of the, as a top view, by neglecting thickness. So whenever we are considering the plane stress system, in plane stress system we are not considering thickness. So by neglecting thickness here, this figure is converted to two-dimensional case, and this is this two-dimensional case in which the thickness is neglected, and by neglecting that thickness, the various component of the stresses that are shown here. Is it okay? So try to understand one by one various components. Once again we will consider here. So here this sigma theta theta, where arrow I am showing here on this particular stress, is this stress along angular direction. This is the stress along angular direction, which is represented by sigma theta theta, which is present on this surface. During Cartesian coordinate system, we have proved about the unbalance. Okay. So what is unbalance? That we have seen in Cartesian coordinate system, and that unbalance is due to the position of any object. Okay. So we have considered this small portion here, and this particular surface on which this sigma theta theta is acting, opposite surface is shown here. This is the opposite surface which is shown here. On this opposite surface, equal and opposite forces by considering unbalance is shown. Is it okay? So here on this surface, unbalance is shown. And what is that unbalance? If this, suppose here it is sigma theta theta, opposite side, sigma theta theta plus dou sigma theta theta upon dou sigma theta theta upon dou sigma theta and d sigma theta. Is it okay? So here we can consider that unbalance dou sigma xx upon dou x dx like this, dou sigma theta theta, dou sigma theta, d sigma theta. So what is meaning of that? Once again, we first of all understand the meaning of this thing. Okay. So if we consider, if we understand the meaning of these things, then we will come to know that this dou sigma theta theta dou sigma theta d theta is the unbalance. So additional plus position is the unbalance. In case of Cartesian coordinate system, the first proof we have seen in that unbalance was shown that dou sigma xx upon dou x into dx, like this it was shown, dou sigma xx upon dou x into dx. So like is present here also, that is dou sigma theta theta, dou sigma theta, d sigma theta, that is present here. Is it okay? So that amount of unbalance is added on sigma theta theta. On this surface, sigma theta theta is present. On its opposite surface, unbalance is added. So sigma theta theta plus dou sigma theta theta, dou sigma theta, d sigma theta. So d sigma theta represents the small portion here, and dou sigma theta theta, dou sigma theta is the partial differentiation of this part. So this unbalance is added here, and by adding unbalance, this particular sigma theta theta that we can observe. Now as far as concerned with this particular surface here, on this surface still two more stresses are going to act, out of which one component will be the component of this theta in z direction and component of this theta on radial direction. Is it okay? But as we are considering 2D and theta, that is and z, that is the thickness we are neglecting, So due to this non-availability of z term, here we are not taking into consideration on this surface. But component of this theta along radial direction, that we must take into consideration, which will be act on this surface, and that will be considered to be sigma r theta. So sigma r theta represents that component of sigma theta theta along radial direction. Okay, so component of this sigma theta theta angular stress along radial direction, so that is sigma r theta. Here we can understand on this surface sigma theta theta is also present and sigma r theta is also present. Is it okay? So this is particular component of sigma theta along radial direction. Similarly, this equal and opposite stress on opposite surface, equal and opposite stress on opposite surface, so that is also shown here, and that represents the sigma r theta plus dou sigma r theta dou theta d theta. Is it okay? So try to understand this thing. Sigma r theta, so that sigma r theta is present here, and additional to this sigma r theta on opposite surface, by adding its unbalance, the second equation on opposite surface will be the stress sigma r theta plus dou sigma r theta upon dou theta d theta. Is it okay? So that also you understand here, that is by adding unbalance, here we are getting this sigma r theta like this. Now here these two surfaces are completed, which are opposite to each other. These two surfaces are completed. Now let us concentrate on remaining two surfaces. In that remaining two surfaces, one surface is inside surface and another surface is outside surface. Is it okay? So here a radius of curvature is shown, here also a radius of curvature is shown. So the surface inside here and surface outside here. So by considering this figure here, we will come to know that sigma rr is the stress along a radial direction, and sigma theta r is the component of this radial stress along angular direction, because we know that this particular direction is the direction of angle, and this component is the radial component, and this particular line is the component of this sigma rr along theta direction. Is it okay? So here we can understand here what is sigma rr and what is sigma theta r. Then equal and opposite to sigma rr, which is moving inward, which is moving inside, but equal and opposite surface which is present here, so in which we will have to add the unbalance. So by adding unbalance here, we can consider sigma rr plus dou sigma rr upon dou r into dr. Is it okay? So try to understand here how the things are happening, how unbalance is added here with the same definition and by changing notations only. The concept is same again here, that is sigma rr is the stress moving towards the center, and sigma this opposite stress on opposite surface, in which we will have to add the unbalance here. Is it okay? So by adding unbalance here, this will become sigma rr plus dou sigma rr dou r into dr, where dr represents the small dimensions along a radial direction. Is it okay? And this is the partial differentiation of stress along a radial direction with respect to radius. So sigma rr, and opposite to that sigma rr plus dou sigma rr upon dou r into dr. So we can understand now these two things. Similarly, sigma theta r, so that represents component of this radial direction along angular direction. Here arrow itself will represent that this is the stress present along a radial direction, angular direction. So sigma rr, stress along radial direction, its a component along angular direction is sigma theta r. Now if we consider the opposite surface, if we go to opposite surface of that, then this sigma theta r which is present here, same sigma theta r with unbalance, that we will able to observe here. Is it okay? We have seen that unbalance may be due to the position or may be due to the some reasons due to which this we are going to take into consideration. So sigma theta r which is moving in the direction, which direction is shown here. So this sigma theta r, component of this r along theta. So for that we are going to add the unbalance. And by adding unbalance on the opposite surface, this will become sigma theta r, sigma r. So here dou sigma theta r, dou r into dr. Is it okay? So sigma theta r plus dou sigma theta r, dou r dr, by considering unbalance here. Is it okay? So here once again these two surfaces. Now initially we have seen that there were two surfaces, but later on now we are considering here the remaining two surfaces, and now remaining only two surfaces are remaining, out of which one surface is the top surface and another surface is bottom surface. Is it okay? So if we go beyond this slide, besides this, here we will come to know this is the surface which is this top surface, and this is the surface which is the bottom surface. So the stress acting on the top surface and stress acting on the bottom surface. So that also we will have to take into consideration here. Now as far as concerned with this top surface, sigma zz is the stress present on the top surface, and it's a component sigma theta z and sigma rz that are present. So sigma rz is the direction, if we see here, this direction is the direction of r, and sigma theta z is the direction along the, this is the angular direction, so radial direction and angular direction. So likewise, by considering these two directions here, we will come to know what is this sigma theta z and what is this sigma rz. Is it okay? So these two stresses are present here, sigma theta z and sigma rz. Here you can try to understand here, sigma rz and sigma theta z. However, this sigma zz we are not taking into consideration, because this is vertical component, and vertical component taking into consideration is difficult, because here we are considering only two-dimensional case. So z thickness we have considered a unit, and we have neglected this thickness, and that's why only we are considering here that sigma rz which is present along the radial direction, sigma theta z which is present along the angular direction, and at the same time its unbalance should also be taken into consideration. Means suppose here we are considering this sigma rz, then definitely its unbalance is also present on the opposite surface, and if we are considering this sigma theta z, then definitely its unbalance is also present on the opposite surface. Is it okay? So let us consider that unbalance also. So sigma rz is present here, and by considering unbalance, sigma rz plus dou sigma rz dou z into dz. Similarly, sigma theta z is present here, and by considering its unbalance, sigma theta z plus dou sigma theta z dou z into dz is present here. Is it okay? So likewise here, by considering unbalance, we are getting here sigma rz and sigma rz plus dou sigma rz upon dou z dz and sigma theta z. So sigma theta z plus dou sigma theta z upon dou z into dz. Is it okay? So here try to understand first of all the stress components with unbalance, without unbalance, and acting on respective locations. Is it okay? So top surface, bottom surface, inside surface, outside surface, and two other surface which are opposite. Hello, am I audible?
Yes, sir.
Okay. So let us see here how many number of components are there now. Just count. Manoj, how many number of stress components are present now? One by one we will have to count them. On this surface, how many these stress components are present? Am I audible?
Yes, sir.
Uh,
Sir, in a radial direction, there is a sigma theta theta, and the component of sigma theta theta in uh, uh,
sigma r theta.
sorry. Uh, Trace along angular direction is sigma theta theta, and the component of sigma theta theta in radial direction is sigma r theta.
Correct. Very good. Very good. So
And
these two components are present on this surface. Okay. Opposite surface, again same two components, means 2 plus 2, this 2 plus these 2, that become equal to
4.
4. Very good. 4. Very good. Similarly, on this surface, these 2,
Sigma
and on
r
another opposite surface, again
2.
these 2. means 2 plus 2,
4.
4. And this 4 and this 4 became equal to
8.
8. And
8.
on this top and bottom portion, by considering top surface and bottom surface, and by considering all this stress component, how many number of these stress components are there?
4 plus 4 plus 4.
4.
12.
4 plus 4 plus 4, exactly. So that will become equal to 12. So 12 number of stress components are present, which we are taking into consideration in order to analyze this polar coordinate system in order to obtain the equilibrium equation. Is it okay? In Cartesian coordinate system also, we have obtained the equilibrium equation, and now in polar coordinate system also we are going to obtain the equilibrium equation. So in order to find this equilibrium equation in case of this polar coordinate system, we are going to take into consideration these 12 stress components which are present here on different positions and locations. Now one more thing we'll have to take into consideration here, that the O, which is the center, here, from this O, this particular body where this inner position of the part is shown here, so from O to this point, the distance considered is R. Is it okay? So from this inner point, O point to inner surface, this distance is considered to be R, and angle subtended by these two surfaces at this origin point O is considered to be d theta. So this angle is d theta, and this radius is R, and this small component we are taking into consideration along radial direction. So that's why this we are considering to be dr. R is radius, dr is the small component which we have selected here. D theta is the small angle which is subtended due to these two surfaces. If we join these two surfaces here at origin, then here one angle d theta will get formed, and this d theta, which is the angle subtended by these two surfaces here. Is it okay? So R is radius, dr is the small component along radial direction, and this d theta is the small angle which is subtended by these two surfaces here. Is it okay? So like this terminology initially we will try to understand here, and then we will go for the analysis of all this by considering this. Here if we try to consider this equation, we will come to know that how each and every component of the stress is taken into consideration.
सर dr कुठं आहे?
So dr म्हणजे हा जो स्मॉल म्हणजे इनर सरफेस इथं सुरू होतो. Here inner surface starts, and here outside surface is present. So this thickness along radius, because we are considering this as a small component, here we are considering this as it is our assumption that we have taken small component. जरी फिगर आपण त्याची मोठी काढलेली असली तरी एक स्मॉल कॉम्पोनंट आपण किंवा एनलार्ज केला असला हा कॉम्पोनंट, तरी तो कन्सिडर करत असताना रॅडियल डायरेक्शन मध्ये असणारी स्मॉल रॅडियल थिकनेस. So this is the small radial thickness along radius, and which is represented by dr. Is it okay? So this is dr, this is d theta. However, z is not present, so that's why dz is not present. So this inner surface to outer surface, in between that, this distance along radial direction. R is exactly radius, and the small component along radial direction is dr, that we have taken into consideration here. Is it okay? Now let us come to one by one each and everything. So on this slide we are observing various stress components. Now we will try to add how many number of components are there. See here, this is the first one, 1, this is 2, this one is 3, this one is 4 here, 5, 6, 7, 8. 8 components are present. However, in this figure we have considered it to be 12 components. So 4 components are going to become 0, and why they are going to become 0, that we will see. But before that, you should see that these 8 components of the stresses which are taken into consideration from reference from this reference figure, and additional to that, one more component which is considered here, plus FR dr d theta dz into bracket r plus dr by 2. So this FR dr d theta dz in bracket r plus dr by 2, that represents the body force, and another 8 component of all these forces are considered to be surface forces. So this total derivation consists of 8 surface forces and 1 body force. However, this particular portion which is taken into consideration, so that is in equilibrium condition. So that's why if we add all these forces, now I am using the word force, is it okay? Because here we have used the word stress. Sigma is the notation of stress. But now I am using the word unbalanced force. I am not using the word stress. So that's why all these forces, these are added here. Surface forces plus body forces, but body is in equilibrium condition. That's why this is equal to 0 here. Is it okay? So here you can understand this particular figure, this particular analogy. And now one by one, we will try to see how these forces are converted, how these stresses are converted into forces and how they are taken into consideration. Now let us come to this first point. So here it is shown minus sigma rr d theta dz r. And let us understand first of all why this is happening. Minus sigma rr. So here you see surfaces. Now these 2 surfaces we are taking into consideration. Always our sign convention is that forces going. Now here this OR, this line we are taking into consideration. Is it okay? So our reference line is here, which is starting from O point and which is ending at this R. So OR line, you are observing now this OR line. This OR line represents the radial direction. So all these component of stresses we are now going to resolve in radial direction, and we are resolving all these component of forces in radial direction because we are trying to get the equation or equilibrium equation in radial direction. Is it okay? So we are interested to find the equation in radial direction. Is it okay? So equilibrium equation in radial direction, that's why we are going to resolve all these component of forces in along R or along a radial direction. Is it okay? Now as far as concerned with each and every forces, if we consider the sigma RR, now this sigma RR on which surface it is acting, you can understand here, this is the inner curved surface, this is inner curved surface. Here you can see this is inner curved surface which is present here also again, this inner curved surface. Now sigma RR which is exactly acting on this OR direction, but opposite to OR direction. Is it okay? OR direction. So this is moving along R, But sigma RR is opposite to that. And as sigma RR is opposite to that direction, so that's why that will consider to be negative. So sigma RR here we are considering negative. Okay, so first of all understand this, sigma RR is considered to be negative. So that's why minus sigma RR. Now this is stress, but we want the force. And we know that how to convert that particular stress into force. For that purpose, because the basic definition of stress is equal to force upon area. So in order to calculate the force, we will have to multiply by area to the stress. So here sigma RR acting on this inner curved surface, and that we are going to convert into the force. So in order to convert that stress into the force, we will have to take into consideration the surface area or inner surface area. Is it okay? So for this inner surface area, what we are considering here is R into d theta. Is it okay? So R into d theta, that represents this inner curved portion. Is it okay? R d theta is inner curved portion. And at the same time, the second dimension is also useful for all of us, because in order to understand or in order to have the area, if we refer this figure here, because we are now observing this particular surface. So for that surface here, this curved portion, if subscribed angle is the intended angle, here it is d theta, and the distance from this axis here it is r. R into d theta will be this inner curved portion. However, this vertical is dz. Okay, so the vertical surface is dz. That stress is acting on this surface. So that's why this stress and area of this surface. So area of that surface will be r d theta dz. Look here, r d theta dz. So r d theta dz. These terms will come. These three terms together will form the area of that inner curved surface, and sigma RR represents the stress acting along a radial direction. Is it okay? So stress acting on radial direction multiplied by this area, stress into area, that gives the force. So that's why these two factors multiplied together will give the force. However, this is acting towards this O, and we are going to resolve along R direction, which is opposite to that. So that's why this is considered to be negative here. Minus sigma RR d theta dz R, that represents the unbalance, that represents the force acting on this inner surface but in a radial direction. Now come to the second point. Second point in that, now it is considered that the opposite force, which is equivalent opposite force of this sigma RR, which is present here. So this equivalent opposite force here, we consider that sigma RR plus dou sigma RR dou R into dr. Okay, with usual notations, unbalance, by adding unbalance, this will become sigma RR plus dou sigma RR upon dou R into dr, which is equivalent opposite here. Is it okay? So by considering that equivalent opposite force here, we will consider sigma RR plus dou sigma RR upon dou R into dr. But this is stress, and in order to have the conversion of that stress into force, we will have to take into consideration the area of this surface. Okay, we will have to take into consideration the area of this surface, and the area of this surface will be considered here with the components which are associated with this surface. Which are the components associated with this surface that we will see first of all. So here once again, if we consider this particular length, now this will be arc length, and this arc length is connected with this R plus dr. Okay, so this distance from this O to this outside corner distance is R plus dr. Okay. Now subtended angle is d theta. So R plus dr into d theta. So that will be this particular arc length which is present at its outside surface. So R plus dr d theta is this arc length. At the same time, dz that will be present here as shown in above slide, because in above slide we have seen that here if we consider this curved portion into this height. So this height is dz and this curved portion is r plus dr into d theta. So this will be this outside arc length. Is it okay? So outside arc length into this height dz. So by considering these two, we will come to know that this d theta, dz and r plus dr is required. Is it okay? So r plus dr into d theta, r plus dr into d theta, that is the arc length, and dz is the height. So that's why this particular area of the surface is required to take into consideration. So sigma RR plus dou sigma RR upon dou R dr by considering unbalanced. So here we can understand sigma RR and sigma RR plus dou sigma RR dou R into dr, how that is taken into consideration. Is it okay? Now let us take example of this sigma theta theta. Now sigma theta theta is present on this surface. Opposite surface is present on this opposite surface. Sigma theta theta plus dou sigma theta theta upon dou sigma theta theta upon dou theta d theta. Is it okay? So try to make correction here that dou sigma theta theta upon dou theta into d theta is present here. So on this surface, this is sigma theta theta. On opposite surface, sigma theta theta plus dou sigma theta theta upon dou theta d theta is present. Is it okay? Now, first of all, we will have to convert that stress into force, and later on that force we have to resolve along r direction. So that is the two things which we have to taken into consideration. So when we considering the stress, or when we are converting that stress into force, then that becomes sigma theta theta into this surface area. So what is that surface area? Here, this is dz and this is dr. So dr into dz will be surface area. So here sigma theta theta into dr dz. But we are going to resolve that. So if we take angle, if I am extending this line here, then what will be the angle of this line sigma theta theta and r? 0 again. So sigma theta theta and R. So in that, if we try to take the angle, then by considering that angle here, so see here, sigma theta theta, dr dz, this is the stress, this is the area. By multiplying with this area to this stress, this will convert into, this is converted now into the force. But in order to resolve in R direction, we will have to consider its a component. So this sigma theta theta will resolve in two components, out of which one will be the cos theta, another will be sin d theta, because here it is total angle is d theta. So if we consider that this surface is making angle d theta by 2, this surface total angle total subtended angle is d theta, but half angle will be d theta by 2. So here if we consider line OR here, so with this OR line, this surface is making an angle d theta by 2. Similarly, this opposite surface is also making an angle d theta by 2. Is it okay? So we are now resolving this sigma theta theta along this R direction. So for this sigma theta theta, there will be two components, out of which will be cosine and another will be sine. So cosine means with this d theta by 2, and sine means in perpendicular direction to that. Is it okay? So in applied mechanics, number of times we have resolved that forces, and that's why we know that concept of how to resolve this. So this sigma theta theta, which makes an angle here, this 90 degree plus d theta by 2. Okay, this angle will be, if we try to take here, this 90 will be 90, this angle will be 90 plus d theta by 2. Is it also d theta, because this is line is, and this line in between that angle is d theta by 2. And same thing is going to reflect here, because this line OR and this sigma theta theta, that are perpendicular to each other, and at the same time, so here O and this surface for this sigma theta theta will be perpendicular, and here this OR line, so for that this central line, that will be perpendicular. So here this angle is going to make, and this angle will be d theta by 2. So which is considered here the sine component of that. So sigma theta theta, dr, dz, and sine d theta by 2. Like this, sigma theta theta is represented. At the same time, this another and opposite stress acting on this another surface, that also we are going to take into consideration. So sigma theta theta plus dou sigma theta theta upon dou theta d theta, this is present on this surface, and it's also one component along this R direction we have to take into consideration. Component of this surface along R direction we are going to take into consideration on this surface, and for that purpose, this next logic we are going to take into consideration that here sigma theta theta plus dou sigma theta theta dou theta d theta dr dz we know. So this component, by adding unbalanced dr and dz, that is the areas. So stress into area, this will become equal to force. And once again here we are considering sin d theta by 2, because if we extend this line here, angle made, we are resolving that in along the direction of OR here. So by considering that, the sigma theta theta dr dz sin d theta by 2 minus sigma theta theta plus dou sigma theta theta d theta dr dz sin d theta by 2. Is it okay? So let us stop with this particular concept here, and for the next lecture we will try to understand the remaining component of forces which are shown in these equations. So before that, anybody any doubt?
No, sir.
Okay. So let us stop here. Yes, thank you. बरोबर. हा, बरं, हा. बरं. ठीक आहे. Clear आहे? बरं, आता लॅबचं काय?